Hello everybody, and a very big thank you to Jabulani Beki Mtembu for a very informative lecture on biogeochemical cycles that highlights the importance of biogeochemical cycling of carbon and nutrients that are able to support life on the planet. My name is Dr. Sandy Thomala, and I'm a senior scientist that works at the CSIR in Cape Town, South Africa. I work with a team of researchers that are all part of SOCO, and SOCO is the Southern Ocean Carbon and Climate Observatory, which takes a multidisciplinary approach to understanding the role that the Southern Ocean plays in the global carbon cycle and how it's expected to change with the changing climate. If you want to find out more about us, please go and check out our website. So my role in the SOCO group is that of a biogeochemical scientist. And as Becky mentioned, this involves research in biology, geology, chemistry, and physics that all together combine to better understand the cycling of elements necessary for life on the planet. So my job today is to provide the critical eye from the science guy. And I've decided to take this opportunity to stimulate critical thinking around some of the topics that Becky put forward in his lecture. In particular, I'm going to focus on the carbon cycle and how changes in this cycle are affecting our planet. So Becky mentioned at the very beginning of his lecture that fluxes are defined as the movement of elements from one reservoir to another. So I'm going to talk a little bit more about the global carbon cycle and in particular about the role that the Southern Ocean plays in regulating carbon dioxide fluxes between the ocean and the atmosphere reservoirs. So let's go backwards a little bit first to explain why it is that we all put so much effort into studying the carbon cycle. Well, I hope by now you all are aware that carbon dioxide is a greenhouse gas and that greenhouse gases are critical to maintaining life on the planet as we know it. And this is because greenhouse gases in our atmosphere allow the atmosphere to heat the earth. So how does this happen? Well, you've got your solar radiation, which powers the climate system. Solar radiation in the form of short wavelengths is allowed to enter the atmosphere. Some of it is bounced back into space, but at least half of it enters and penetrates our atmosphere and heats the Earth's surface. In return, heat from the Earth's surface is re-radiated from the Earth into the atmosphere, and some of the infrared radiation passes through the atmosphere, but most of it is absorbed and re-emitted in all directions by the greenhouse gas molecules and clouds. And the net effect of this is to warm the Earth's surface and the lower atmosphere. So greenhouse gases are good because without greenhouse gases in our atmosphere, our planet would be too cold to support the life as we know it. However, the problem is that too many greenhouse gases in the atmosphere are now causing the atmosphere to be warmer than it has been in previous years. This is a slide or a graph that shows time on the x-axis and carbon dioxide increasing on the y-axis and simultaneous increases of radiative forcing on the other y-axis. And this goes to show how the present day increases of CO2, which are now higher than they have been in the past 650,000 years, are causing an increase in radiative forcing, which in turn is increasing the temperature of our planet. Now, I want us to think a little bit more about what the implication of these changes are. So generally speaking, carbon wouldn't have been locked into the Earth's crust for millennia, but here we are digging it out and burning it and releasing the CO2 into the atmosphere. So what effect is this increased CO2 having on our atmosphere other than increasing our temperature? So here is a table from the IPCC report, which shows that the emissions of CO2 from fossil fuel burning are 6.4 petagrams of carbon per year. 1 petagram of carbon is equivalent to 1 billion tons. But despite that fact that we're putting 6.4 petagrams of carbon into the atmosphere every year, we're only seeing a measured increase every year of 3.2. So what's happening to the other half of the CO2 flux that we're putting into the atmosphere? Well, fortunately for us, both the land and the oceans are able to take up some of this excess CO2. Over here we can see that the land to atmosphere flux is -1. This negative means that the net effect of the CO2 flux is from the atmosphere into the land. This land flux is comprised of land use change and land sink, and you can see that the land use change is positive, and this means that land use change is resulting in a flux of CO2 from the land to the atmosphere, and this is from cutting down trees and replacing a lot of photosynthesizing plants with industrial buildings and concrete. If you look at the ocean to atmosphere flux, it's -2.2. And this shows that the oceans are the most important sinks of CO2 that are accounting for buffering this impact of CO2 into the atmosphere. So how are the oceans managing to do such a good job of taking CO2 out of the atmosphere? Well, there's two ways it does it. One is called the solubility pump, and the other one is called the biological pump. The solubility pump is driven by thermohaline circulation, which has got to do with the temperature and the density of water masses. If you have very cold water masses at the poles, cold water has a higher ability to dissolve CO2 in it. Cold water is also much denser than warmer water. So at the poles, you have very cold water, which is able to dissolve high amounts of CO2, so it has a high CO2 content that sinks. When this water upwells to the surface, the water gets warmed and the CO2 is released once again to the atmosphere. The biological pump is driven by single-celled plants in the ocean. These single-celled photosynthesizing plants are called phytoplankton. So this is a small diagram that explains the biological carbon pump. So here you have your phytoplankton, which are single-celled plants, which are photosynthesizing with the use of sunlight, and they are fixing CO2 from the water into organic carbon in their tissues. These phytoplankton are then eaten by zooplankton and bacteria, and they die and sink, and the particulate carbon is exported to the deep ocean. This creates a partial pressure differential between the atmosphere, which allows more CO2 to be fluxed into the ocean. So this is the biological carbon pump. Over here we see a figure from Takahashi 2009, and it shows the mean annual air sea flux. And so this figure is showing you where CO2 is fluxing into or out of the ocean. Green is neutral. Anything in the orange colors shows that CO2 is fluxing out of the ocean, and all the blue colors shows where CO2 is fluxing into the ocean. So over here in the Southern Ocean, you can see there's a huge area where the CO2 is fluxing into the ocean, and the Southern Ocean is the largest ocean that's responsible for the majority of the ocean CO2 flux into the ocean. Here, though, you can also see that there's quite a large region where CO2 is fluxing out of the ocean. So I'm going to display this a little bit more in detail. Here's a section of the Southern Ocean from Antarctica to 40 degrees south. The solubility pump you can see here is cold water that has got a high CO2 content, which sinks down. The cold water here is also moving north, and it's sinking underneath intermediate water, and it's taking CO2 with it. Over here you can see the single-celled plants, which are photosynthesizing, and when they die, they take their CO2 with them. Over here you can see deep water, which is old and has very high CO2 content, which is upwelling, and when it reaches the surface, it's outgassing and releasing the CO2 to the atmosphere. So this is a similar section, which has the Antarctic continent on the left, and it moves north to 40 degrees south on your right. And here you can see zero, which means that the flux of CO2 is in equilibrium, so it's neither fluxing in or out. And this line is showing the net flux of CO2 from Antarctic zone all the way to the subantarctic zone. And what accounts for this change in flux with latitude? So over here you have, down south near the continent, you have high biological production. And you also have the formation of Antarctic bottom water, which is cold and dense and is sinking. So there's a high flux down of CO2 into the ocean. But here you have circumpolar deep water, which is high CO2 content, and it's upwelling, and it's coming into direct contact with the atmosphere, and it has a deep water outgassing of CO2 into the ocean. So the combination of this flux in and this flux out means that the Antarctic zone is quasi in equilibrium. So there's almost as much going in as there is going out. As you move further north, though, here you've got the subducting of subantarctic mode water and Antarctic intermediate water. Both of them are subducting these high CO2 contents down, and on top of this, you have very high biological production. So both of these fluxes are fluxing the CO2 into the ocean, which is why you have a strong CO2 sink in the subantarctic zone. Okay, so this is a bit of a boring slide because all it has is writing on it, but I wanted to remember to tell you that there are two ways that the oceans are able to mediate atmospheric CO2 increase. One is through the uptake of anthropogenic CO2, so man-made fossil fuel-released CO2 exchanges, but the other one is the natural exchange of CO2, and this is the exchange of CO2 that the oceans and the land of the atmosphere have been having for millennia. Now, the magnitude of the steady-state anthropogenic CO2 uptake, which is linked to increasing CO2 emissions, is very well constrained. The problem is that the magnitude and the trends of the non-steady-state driven changes in the natural CO2 fluxes are not very well understood. So given that we know that the temperature of the planet is going to increase due to all the CO2 that we're putting into the atmosphere, here's a figure that shows 3 different models predicting how the temperatures are going to change up to 2099. If we know the temperatures are going to change, how do we suppose that the predominant winds are going to change? And if we know that the predominant winds are going to change, what influence are they going to have on the ocean currents? And since we know the ocean currents have got deep water masses that have high CO2 concentrations, what would happen if we change the currents and upwell more water to the surface that will change the flux of CO2 out of the system? So that would be what's going to happen to the natural CO2 fluxes, not just the uptake of the anthropogenic ones. So this figure basically summarizes the point that I was trying to get across from the beginning, and I hope I've managed to do that. And what this figure shows is the carbon cycle, but it separates out the natural CO2 flux from the anthropogenic CO2 flux. And the take-home message that I wanted to get across from this figure is that the anthropogenic CO2 flux is much, much smaller than the natural one. Here you can see it's almost in balance, this anthropogenic flux, and so is the natural flux, but the natural flux is much, much higher than the anthropogenic CO2 flux. In addition, I want you to take note how much CO2 of the natural CO2 is stored into the oceans compared to the anthropogenic. Now, what happens if this increase in temperature of our planet changes the wind cycles, which changes the currents, which end up upwelling more of this ocean water, which is rich in CO2, to come into contact with the atmosphere? That would result in a huge outgassing of CO2-rich waters into the atmosphere, which basically could turn the Southern Ocean into more of a source of CO2 rather than currently a very big, strong sink of CO2. And this would have really serious risks to the effectiveness of the projected global emission cuts that we have currently. So reducing the number of aeroplanes that fly will have very little effect to reducing the amount of CO2 if this system has to change. So this highlights why we need to put so much effort into understanding not only the anthropogenic CO2 flux, but also to understand the natural CO2 cycle, and to understand if we start changing the forcings of temperature and winds and currents, what do we expect the response of the natural CO2 system to be in a non-steady state? So I hope I managed to do okay with that. I found it very difficult to video myself. I think I'm much better in real life. But anyway, I hope I've created some questions that will make you think and hopefully cause you to Google a bit more and to research a bit more and find out more about how important it is to understand the fluxes and the cycling of elements in our planet. Thank you.